we're going to look at the specific type of rate of change which is known as growth and decay. To start off with, we're going to look at a very, very simple model, and it works on this basic idea. Growth and decay is directly proportional to population. I mean, the more people you have, then the more people that are going to get born, the more people that are going to die. I mean, that's the basic idea. So we could write it like this then. If it's directly proportional, it must be equal to some constant times the population. So the P to T would equal to some constant times the population. Now later on next year we'll see how we can actually solve this, what we call differential equation. But for now it's okay to just quote the solution. And the solution to it would be this. P would end up equaling some constant, just call it A, e to the power of kt. So at this stage they won't ask you to find the solution, they might ask you to prove it, and we can do that. But they won't ask you necessarily to find it. So P, which is representing population, A will end up being the initial population, because if you look at the equation, if you make T equal to 0, you're going to end up with e to the power of 0, which is of course 1, and so population would be A. So A is always the initial population. K is our growth constant, or if it's dying, it would be a decay constant. And T, of course, represents time. So here's how we could prove it if they ask us to do so. We actually start with the answer, and we're going to show it satisfies this differential equation. So P is equal to AE to the power of KT. Now we saw when we differentiate exponentials, we differentiate the power. Differentiate KT, any constant times T, we'll just get K, we'll just get that constant. So we bring that to the front and we get K A e to the KT, but hang on, P is A e to the KT, so we have K times P. So it's a very simple little proof. We just have to differentiate it once and then go, oh look, this is in fact K times that initial equation that we had. The growth rates per hour of population of bacteria. 10% of the population, that's its growth rate. Initially we have, how many zeros are there? 1 million. We have 1 million of these bacteria. Standard sort of first question then, just like we did in our theory there, show that this is a solution to the differential equation. Okay, so we start with the equation, differentiate this, well, this time the power is 0.1t. Differentiate 0.1t, we get 0.1. So bring that to the front. And we have, oh yeah, look at that, we've got 0.1 times the original equation itself. So we do have 0.1 times P. So yes, it is a solution to our differential equation. Now it becomes a substitution question, really. Determine the population after 3.5 hours. Well, we need to work out what A is. A, remember, was the initial population. So we end up with 1 million e to the 0.1 t. Substitute in the 3.5 to 4 significant figures, I get 1,419,000. But again, we answer the question. So I write some sort of statement at the end to answer the question. So after 3.5 hours, we've got 1,419,000 bacteria. Okay, let's do a different one. This time we're decaying, it ends up. So on an island, the population in 1960 was 1,732, and in 1970, so 10 years later, it's 1,260. So the population is decaying. They mustn't like each other or something. They're all killing each other. Find the growth rate, well, they're calling it a growth rate. It'll turn out to be a decay rate, assuming it is proportional to the population. So we can assume that the rate of change, the P to T, is a constant times the population. We're allowed to jump to the answer and go, oh, well, that means P must equal AE to the KT. Now, the initial population, so it's not when T equals 1960, it's still T equals 0, it's 1,732. So there's my equation. P equals 1,732 e to the KT, but K is what we want to find here. We don't know what the rate is. But they have told me that 10 years later, so when T equals 10, the population is 1,260. Let's make K the subject of this exponential equation. Play around with it, and there is 1/10 the log of 1,260 over 1,732. So we can store that number in our calculator. That's going to be our K. It's roughly that. So negative 0.0318165. So the growth rate is negative 3%. So it's actually a decay. It's actually a decay rate because it's negative. But answering what they've asked for a growth rate. So all right, the growth rate is -3%. So in how many years will the population be half that in 1960? So how long does it take to the population to half? Well, half would be 866. So that's what we're asking. When is it 866? This is the equation we have to solve. Now, interestingly at this point, for those of you that do, was it physics or chemistry, you talk about half-lives of radioactivity. And you might have seen a similar formula to this, where it's 1 over k log of a half. Well, this is where it comes from. So e to the kt would equal a half, rearrange that, make t the subject. We get 1 over k log of a half. As long as we know the growth, or in this case decay rate, we can work out the half-life. So sub in that k, which we just found, t is 21.786. So the question is, in how many years? Well, it'll be in 22 years. Interestingly, if that had come out to be 21.286, I would still say in 22 years. Because in 21 years, it hasn't halved yet. There's still more to go. 16b, we'll have a go at some growth and decay questions.